Hey guys! Alright, now we're going to do Chapter 7, Section 5, which is on independent events. So, on our notes it says, if one trial of an event does not affect the probabilities of future trials, then the trials are said to be independent. So we've got independent and dependent events. We're going to learn about dependent events a little bit later on, but for now we're just going to talk about independent events. And basically what that means is that as long as you have two events occurring that don't affect each other, they're considered independent. Which makes sense because dependent means that it would rely on the other event, and if something doesn't affect another event, it would be considered independent from that event. Okay, so some different types of independent events would be things like coin flips. Okay, I know that if I flip a coin, it's not going to affect whether I get heads or tails the next time, right? It doesn't change the probability of actually getting heads or tails. Another thing would be spinning a spinner, doing any sort of sampling with replacement, so as long as you're putting that item back, it's not going to affect what you're going to get the next time. Now, of course, you should make sure that you are shuffling those items. So, for example, if you pull out a card and you put it back on the top of the deck and then you draw from the top of the deck, well, that's not really a random sampling, okay? And also dice rolls. So if I roll a dice, I know that if I get a 6, that's not necessarily going to change what I get the next time. Alright, as you will see later though, this does not mean that questions cannot be written using these examples in which the situation is actually not independent. Okay, so basically what I'm saying is that the book and me will try to trick you, okay, and you'll maybe think that these are going to be independent events just because it's a coin toss, but that's not necessarily true. Okay, we actually have to use a formula to prove that something's independent. We can't just say, duh, it's independent. Okay, so events A and B are independent if and only if the probability of the intersection is equal to the probability of A times the probability of B. So, to prove that something's independent, we can say that the probability of their intersection is equal to the probability of A times the probability of B. Alright, so that's the formula that you want to use in order to prove that something is independent. Alright, so let's look at problem number 5, which says, consider two trials of rolling two dice. Let A equal getting a sum of 6 on the first trial and B equal getting a sum of 8 on the second trial. So essentially what I'm doing is I've got two dice and I'm going to roll them and I'm going to roll them again, okay, and it's asking me what is the probability of getting a sum of 6 on the first roll and then a sum of 8 on the next roll. So right off the bat I need to think about, logically, would those events be independent or dependent? Would it actually affect what I get on my second roll if I get a 6 on my first roll? And the answer is that it shouldn't. It really should not affect that. So this is one of those cases where you can actually just automatically off the bat decide that this is going to be an independent event. Okay, so these events are going to be independent of each other because there's just no possible way that you could roll one set of die and then the same set of die again, and that first roll is going to affect the next roll. It's just not going to happen. Okay, so the first question, it says, are the trials independent? We're going to say yes. Yes, they are independent. Okay. Then it wants to know what's the probability of A intersect B. So in other words, it's saying what's the probability that I actually do get a 6 on my first roll and an 8 on my second roll. So it's not actually saying what is the intersection of getting an 8 and a 6, because we know that that would be 0. There's no way that you could do that at the same time. It's saying what's the probability that I get a 6 on my first roll and then I get an 8 on my second roll. So that's not really a probability that we can just kind of determine by looking at our dice chart. So what we're going to actually use is we're going to use the fact that we know that this is going to be an independent event. So we're going to use this formula here. So we can say the probability of the intersection of that formula is going to be the probability of A times the probability of B And all we need to do is figure out what the probability of A and what the probability of B is. So my A, that is getting a sum of 6 on the first trial. So if I roll 2 die and I get a sum of 6, what's the probability of that actually happening? Well, if I look on my dice chart, I know that that's a probability of 5 out of 36. Okay? Then if I look at B, B is getting a sum of 8. Okay, so again, I'm going to look at my dice chart and I'm going to notice that that is also 5 out of 36. So what I can do is I can actually just multiply these together, and that's going to give me the probability of the intersection, meaning that I get a 6 on my first roll and I get an 8 on my second roll. So if I multiply these together, I get 25 over 1296, and that's going to be the probability of the intersection of these two sets. Alright, the next question says, when Tom shoots free throws, he makes the first shot 65% of the time and the second shot 70% of the time. What percent of the time do both free throws need to be made in order for these events to be independent? So in other words, what they're asking us is they're saying, just assume that these events are independent, and assuming that they're independent, go ahead and calculate what the intersection of those events is. So we know that we can assume that the probability of A intersect B is going to be the probability of A times the probability of B. So I can use that formula again, and I can say, to find this, I'm going to do my probability of A, which I'm going to say is 0.65, times my probability of B, which is 0.7. So I'm just going to multiply those two together, and I'm going to get 0.455. So in other words, if those events are independent, that means that the intersection of those events is going to be 45.5% of the time. Okay, so he would make that shot 45.5% of the time. He would make both. He'd make 65% of his first shot 65% of the time, and his second shot 70% of the time. When those would intersect, that would occur 45.5% of the time, as long as these events are independent. Alright, so we've talked about independent events. Now we need to talk about dependent events. If one trial affects the probability of future trials, then the trials are dependent. So in other words, if I change something and that's going to change the probability of my future trials, those are considered dependent events. One example that I always use for dependent events would be like if you're drawing a card and then you just keep it in your hand. Okay, well, we know there's 52 cards in a deck. If I draw a card out of the deck, now there's only 51 cards in that deck, and the card that I have in my hand can't be part of that probability anymore. So it's going to change the probability of drawing specific cards. Okay, so number 7 on our notes says, consider one trial of rolling 2 die. A is the first die shows a number less than 3, and B is the sum of the 2 rolls is less than 5. So this is a little bit different than the first question we did, because in this one I'm just rolling the dice once. Okay, so I have 2 die, I'm rolling them once, and these things are happening at the same time. So the first die shows a number less than 3, and the sum of the 2 die is less than 5. Okay, so I want to figure out, are these actually independent or not? And I can do that by using my dice chart. So I'm going to follow this formula again. I'm going to say the probability of A intersect B is equal to the probability of A times the probability of B. And I'm going to use this formula to determine if these events are independent. So the first thing I want to do is find the probability of A. So the probability that the first die shows a number less than 3. Well, if I look at my dice chart and I count up all the examples where the first die is less than 3, I'm going to get 12 out of 36. Okay, now I need to figure out the probability of B. So I'm looking for the probability that the sum of the 2 die is less than 5. Okay, well, if it's less than 5, that means that it's either a sum of 2, 3, or 4, And that would give me a total of 10 out of 36 for that probability. Okay? Now I need to actually think about what my intersection is. Okay? Now, in order for these trials to be independent, if they're independent, then it should follow this formula. Okay, so I should just multiply these out and simplify and all that stuff, and I get 120 over 1296. So if they're independent, that's what my intersection is. But with this, I can actually calculate my intersection, okay, by just looking at my dice pairs that fall into both categories. So when I look at my list here, I can see that 1, 1 would fall into that category because my first die is less than 3 and I have a sum less than 5. 1, 2, 1, 3, 2, 1, and 2, 2, all of those things would fall into that category. So that would give me a total of 5 events that would fall into the intersection, which would be 5 out of 36. So now I need to think about, are these events actually independent or are they dependent? And the way I do that is I compare what my probability should have been to what my probability actually is. And I notice that they are different, therefore these are actually dependent. All right, that's everything for section 5.